Every modern motherboard functions as a dynamic, high-precision power conditioning system. Its complex grid of copper wiring serves a singular purpose: managing the hazardous flow of raw electricity toward the center of the board. At the center of this system sits the central processing unit. Modern silicon processors operate on a low voltage profile, typically around 1.5 volts, but they demand massive electrical flow, often pulling upwards of 45 amps of current to execute billions of calculations per second. This creates a massive engineering gap. The computer's switch mode power supply, or SMPS, provides a flat 12 volts of direct current, a level far too high for delicate circuitry to handle. Feeding raw 12-volt power directly into the microprocessor's internal pathways would breach microscopic transistors instantly. Without a transformation stage, the CPU would physically burn out in a fraction of a second. To manage this transition, engineers place a dense array of inductor coils, capacitors, and silicon control chips in a tight perimeter around the CPU socket. This perimeter is the voltage regulator module, or VRM. It is the mandatory engine that steps down voltage while stepping up the current, making the operation of high-performance silicon physically possible. Motherboard power delivery is strictly tiered, partitioning electricity based on a component's specific role and data bandwidth requirements. This block diagram shows the internal hierarchy of an integrated motherboard. High-speed traffic flows between the CPU, RAM, and the North Bridge, while legacy components draw power directly from lower voltage lines provided by the main power supply. The CPU cannot use these direct lines. Because its current draw spikes and drops wildly depending on the processing task, tying it to the main power rails would destabilize the rest of the board. To prevent this interference, the motherboard architecture isolates the CPU into its own dedicated power domain. Within that isolated domain, the 12-volt SMPS supply hits the drain terminal of a power MOSFET, the primary switching engine. It chops the incoming source by switching thousands of times per second. To stabilize this harsh square wave, it passes through an LC filter. The inductor coil resists rapid current changes, dulling sharp voltage spikes. Simultaneously, the capacitor stores charge during peaks and releases it during valleys. Working together, they transform the noisy signal into a pure, low-voltage DC stream suitable for the CPU. These components effectively step down the voltage, but they are dumb circuits. They require an external logic layer to tell them exactly when to pulse and how much power to deliver. This schematic details the logic layer that governs the MOSFET gates. The buck IC and oscillator work in tandem to regulate switch and speed, ensuring the power components respond to the CPU's changing needs. The pulse width modulator inside the buck IC controls the duration of each electrical pulse. By adjusting how long the MOSFET stays on in each cycle, the PWM regulates the final voltage with surgical precision. To manage 45-amp current loads without overheating, motherboards use phase control. They distribute the load across multiple MOSFET groups running in parallel. The oscillator IC staggers the firing of these phases in a specific sequence. As one completes a pulse, the next initiates, ensuring a continuous flow. This makes the VRM a multi-cylinder power plant. It coordinates independent power phases through precise logic timing to maintain stability under extreme current demands. The motherboard boot process follows a strictly deterministic sequence of 9 gates and power shifts. Look at the initial wake-up path. The system sends a tiny 0.85-volt signal to the processor. The CPU returns a voltage sense signal to the Super I/O chip, which converts it into a voltage identification signal and routes it to the buck IC. The buck IC receives this code and immediately adjusts its internal frequency to match the exact voltage and current requested by that specific CPU. Half of the power delivery process is purely mathematical communication. This handshake occurs before any massive electrical load is ever released. Once the parameters are set, the logic triggers the driver ICs, which fire pulses into the gates of the parallel MOSFET groups at the calculated frequency. This initiates primary power delivery. The high-spec current flows through the LC filters into the processor. Once it receives the correct supply, the CPU makes the feedback signal active for the buck IC, confirming stability. After verifying this feedback, the buck IC generates a power good signal for the Super I/O chip, indicating the electrical environment is safe. In the final step, the Super I/O chip pulls the SMPS green wire to logic low, locking the power supply into its on state and completing the boot. A successful startup represents a self-correcting electronic circle. If any signal fails to report, the VRM aborts the process to protect the delicate silicon. When a computer cooling fan spins briefly and then completely stops, it signals a failure in the VRM feedback loop. One of the 9 logic gates failed to resolve, causing the logic layer to cut power. Diagnosing these failures requires following the engineering path we just established, beginning with the 12-volt input from the power supply. Check the LC filter components next. Electrolytic capacitors are common failure points. They age at a temperature-dependent rate and can bulge or leak, causing voltage instability. If the capacitors are healthy, you move to the MOSFETs. A shorted MOSFET prevents the logic signal from reaching the CPU, breaking the power-on sequence. Failures can also occur in the logic layer itself. If the buck or oscillator ICs are heat damaged or have dry solder joints, the board will provide incorrect voltages or fail the post sequence entirely. A motherboard is a deterministic network where logic precedes power. By tracing the 9-step sequence, any hardware failure is isolated to its specific component.